Standard enthalpy of formation and reactions. So the standard enthalpy of formation, delta H, the F stands for formation and the 0 stands for it being at the standard state, is the reference point for all enthalpy expressions. A standard state just means that it's at 1 atm. So the standard enthalpy of formation for any element in its most stable form is 0. So for oxygen as O2 gas, the standard enthalpy of formation is 0, but for ozone, O3, the standard enthalpy of formation is 142.2 kilojoules per mole. So it's only when it's in its stable form. We can define the standard enthalpy of formation for a compound as the heat change that results when 1 mole of the compound is formed from its elements at a pressure of 1 atm. So table 6.4 on page 225 lists the standard enthalpy of formation values, and they would have to be given to you on the test as well. The only ones that would not be given to you are the elements that are in the most stable form, because you should already know that those would be 0. So using the standard enthalpies of formation, we can calculate the standard enthalpy of reaction, or delta H Rxn. Again, Rxn is for reaction and the 0 is for the standard state. So if you look at it, you have the moles, the coefficient, times the standard enthalpy for the products, minus the coefficient times the standard enthalpy for reactants, and then we're going to subtract them. So if you have more than one product, you have to add those together. If you have more than one reactant, you add those together, and then you can subtract. So for example, benzene, which is C6H6, burns in air to produce carbon dioxide and water. So we need a balanced reaction. Calculate the heat released in kilojoules per gram of the compound reacted with oxygen. The standard enthalpy of formation of benzene is 49.04. So they're giving us the benzene because that's not on page 255. So we're going to say delta H of the reaction is equal to, and then we want to look at our products. So we have carbon dioxide, and that is a negative 393.5. Now there's 12 of them, so we want to make sure that we multiply that by 12. Plus, we have 6 waters, and notice that it's specified that water is a liquid, because depending on what state it is, those values can change. And we have 6 of those, minus our our reactants. So we have benzene, and we have 2 of those, plus we have 15 oxygen, but oxygen is going to be 0 because it's in its standard state. So our standard enthalpy of reaction is negative 6534.88, and that is kilojoules per mole. The question asked to calculate the heat released in kilojoules per gram. So we're going to take our heat of reaction, which is kilojoule per mole, and 1 mole is the molar mass of C6H6, 78. So per gram, it's negative 83.78 kilojoules. Hess's law is when the reactants are converted to products. The change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. So calculate the standard enthalpy of formation for carbon disulfide, CS2, from its elements, and then it gives us the step. So if we think about what the reaction would look like, we would have carbon and sulfur added together to form CS2, and then to balance it we would have to have 2 sulfurs. So we want carbon to be a reactant, which it is right here. So we don't want to flip the first reaction. We want sulfur to be a reactant, and it is right here. However, we want 2 sulfurs, so I'm going to have to multiply everything by 2, including my heat of reaction. And then we want CS2 to be a product. And there's a typo down here, I just saw it. There should be a 2 there. Alright, so we want that to be a product, so we need to flip this reaction. And that means we're also going to flip the sign for the heat of reaction. So now we have a positive 1073.6 kilojoules per mole. And then if we look, things that we don't want should cancel out. So 2 SO2 cancels, CO2 cancels because they're both reactants and products. I have 1, 2, 3 oxygens as a reactant to cancel the 3 oxygens as a product. So that leaves me with carbon, 2 sulfurs, and CS2. So if I add these 3 reactions together, I would have carbon, 2 sulfurs, giving me CS2. So now I'm just going to add my heats of reactions together, making sure to multiply by 2, and then using the reverse sign, a positive 1073.6. So my heat of reaction for the formation of carbon disulfide would be 87.3 kilojoules per mole. Now, heat of solution and dilution. The heat of solution, or the enthalpy of solution, is the heat generated or absorbed when a certain amount of solute dissolves in a certain amount of solvent. So this is the same thing that we've been doing as a reaction, except instead of having a reaction, it's just the process of dissolving. So you have the heat of solution, and that's equal to the heat of solution minus the amount that it takes for the components, your solute versus your solvent. If the heat of solution is positive, then it's an endothermic process, and if the heat of solution is negative, then it's an exothermic process. The lattice energy is the energy required to completely separate 1 mole of the ionic compound into the gaseous states. So the U right here represents the lattice energy. Once the solute particles have been surrounded by water, then we have to look at the interaction between the positive cation in the water and the negative anion in the water, and that's what delta H of hydration is. So if we add those two together, then we would get delta H of the solution. This is very similar to what we've been doing before. For dilution, it's the same thing. So diluted just means you have more solvent added to lower the overall concentration of the solute. So the heat of dilution is the heat change associated with the dilution process. So you're looking at the difference between what it was before you diluted it and what it was after you added more of the solvent. So this kind of explains why we always add acid to water. Diluting it with water releases, or diluting the acid with water releases a considerable amount of heat to the surroundings. So this process is so exothermic that it could cause the acid solution to boil and then splatter, which could cause burns and harm to us. So we always do what we oughta, and we add acid to water.